Oops. Hi, everybody. Thanks for joining us today for our panel discussion on communication and coordination at the Chandra Frontiers in Time Domain Science. Our panel today features 4 speakers, and we will have a moderator who is Ada Nebo, coming to us from Observatoire Astronomique de Strasbourg. In addition to being an astronomer there doing science, Ada has also worked at the Strasbourg Astronomical Data Center and is the chair of the Time Domain Interest Group of the International Virtual Observatory Alliance. And I will turn over the spotlight to Ada now.
Thank you. So thanks for the introduction and for all your work, which made possible this meeting. So let's welcome our first panelist, who is Gregory Sivakoff, Associate Professor at the University of Alberta in Canada, and who will share with us experiences with SmartNET and Chandra, a community self-organization for simultaneous observations.
Thank you very much. It's my pleasure to speak to you today on a subject that is near and dear to my heart, and that is organizing large groups of people to try to observe the same objects all at once. So today I'm going to be talking to you about SmartNET. Now, I'll be honest, I'm not the person in charge of SmartNET. The people in charge are actually Matthew Middleton, Enrico Bazzo, Pier Giorgio Casella, and Poshak Gandhi, but I was the one that is in the most convenient time zone. So when we think about simultaneous multi-wavelength astronomy, there are a couple different ways you can approach this. You can think about the correlated timescales, you can think about the electromagnetic frequencies, or nowadays even the multi-messenger aspects, and you can think about the different scientific objects that we study. Oftentimes, we began our work in the field normally by our electromagnetic wavelength. Over the last several decades, we've sort of gone and changed ourselves to be more organized around our scientific disciplines, our objects of interest. This is a plot from a Lorentz Center meeting on simultaneous multi-wavelength astronomy, where it was trying to capture some of the scientific topics where simultaneity actually matters. And you can see that we have correlated timescales down from 100 milliseconds up to year-long timescales. And many of the objects here are the objects you sort of expect from high-energy astrophysics, and thus are absolutely absolutely commensurate with Chandra and its mission. I will say that this is not everything, of course. There are objects missing here. For instance, some of the stellar astronomy we learned about yesterday could very well also be added to this plot. Now, we organized ourselves in the past largely based on the different groups that were doing this. And at each new science group, you might have a collaboration, you might have a electronic organization like the Gamma Ray Circular Networks, you might have several organizations like Mansi are going to talk about with Growth and ZTF. And some of the original ones began with thinking about how to observe AGN with AGN Watch. What we're trying to do nowadays is not just approach this from a what's my individual scientific area, but thinking about this as the community of people that are interested in simultaneous multi-wavelength astronomy. And when I'm interested in multi-wavelength astronomy myself, I tend to be interested in an object like V44 Cygni, this black hole X-ray binary. And in a black hole X-ray binary, most of the time, the material that's being stripped off the donor stays in the accretion disk, but when viscosity changes, large amounts of material can be dumped onto the black hole, leading to a high X-ray emissivity, occasionally relativistic jets, and disk winds, as is shown here from this animation. And the source, eventually, the viscosity will change, and we'll go back to not seeing it as a bright X-ray, radio, optical, etc. source. Now, V44 Cygni was asleep for a little bit over 26, almost 27 years, when it woke up in 2015, and it really kicked up a fuss. And we organized ourselves along slightly new but still fairly old ways to observe this source. And we did this very much in an ad hoc manner. We used social media, we used mailing lists, like the multi-wavelength coordination mailing list that had 114 messages at least. I swear I was only responsible for 28 of them. 132 different subscribers. Tom Marsh was kind enough to set up an area where we could dump when we were making observations to start planning our observing windows. And in many ways, I think this was sort of the beginning of us trying to rethink how we actually are going to do multi-wavelength astronomy going forward. Now, why all the fuss with V44 SIG? Well, what I mean by the fuss is that there were actually 68 astronomer telegrams, 15 gamma ray circular networks, and at the time of the outburst, 3 press releases. There's been more since then. This object was interesting because we knew a lot about it, but more importantly, I think this captured our attention because we had new facilities and new capacities since the last of the great black hole X-ray binary outbursts. These tend to occur about once a decade. And in particular, what's most interesting for today's talk is we had new modes of collaboration and communication. Now, we got great broad multi-wavelength coverage. So this is actually a plot from the database that Tom Marsh helped us create, I should say, which shows that we had observations across the entire electromagnetic spectrum. We had everything, all the different types of modes you'd expect of observations, and we had a lot of simultaneity. Some of the simultaneity was very much enabled by individual instruments, like Integral. Thank you very much for staring at this object for as many days as you did. And that gave us pictures like an X-ray and optical image that is strictly simultaneous from one instrument. And you can see that this source is, even in outburst, an extremely variable source, which made this, of course, very, very interesting. But it wasn't just single observatories. You also had the ability to combine multiple observatories. So this is a picture from my collaboration's work to look at the radio through sub-millimeter jets, all with 4 different instruments at the same time. And we actually have 9 different frequencies of data on this plot. And you can see a huge amount of data. And it turns out that we even came up with a physical model that explains all of this data with a mere 52 parameters. But this is sort of what you can do if you have simultaneous astronomy. How do you do it? Well, as I said, a lot of this came about in 2015, but it wasn't just because of V44 SIG going to outburst. Almost as if we were prescient, that summer there was a Lorentz Center conference paving the way to simultaneous multi-wavelength astronomy. And it occurred basically, so it was in just a few weeks after V44 SIG went into outburst. And at that meeting, we basically realized that what we wanted to do is we wanted to have a way to better organize ourselves so that it's not quite as chaotic as it was the last time. And so this is basically trying to go from the first generation where it used to be call up your friend, tell your friend, to the second generation when we had astronomers, telegrams, gamma ray circular networks, to the third generation when we were sort of using social media, to the 4th generation where we're creating tools specifically for this. And as Erik Kuulkers will be talking about, we're already looking forward towards the 5th generation of how you do communication. But I'll concentrate on this 4th generation and talk about what SmartNET is. And basically, it is just meant to be a tool to help observers to self-organize. The 2 main aspects, in my mind, of SmartNET are the campaign alerts, which basically act like social media fora. Each individual alert is its own discussion. And what happens is everyone that signed up for SmartNET gets alerted when a new campaign alert is started. And then it's up to you to decide whether you want to follow that campaign alert or to completely ignore it. The other very useful bit of information, I think, is, borrowing on the idea of social media, are actual user profiles. In addition to and I'll talk about campaign alerts and user profiles in the next 2 slides. In addition, there are things like VO protocols that we talk about. There's also, we have file sharing, both in public and private modes enabled, although most people aren't using that yet. And we also decided to collate a lot of information that is useful when you're trying to plan these observations. Target of opportunity forums, the visibility tools that people have out on the web, links to meetings, when the guest observer cycles are, all the things that you might need to plan the campaign from its inception of an idea all the way through the publication of the data. So this is what a typical campaign forum looks like when you go to one of these campaigns. In addition to the discussion section, a key aspect are the campaign timelines. And so what's shown here is a tool that Enrico Bazzo created based off basically the idea of Tom Marsh's thing, where we gave him a bunch of data of when our observations began and when our observations ended. And so what happens is you can see that there is a Google spreadsheet that you fill out. That Google spreadsheet populates a tool which you can zoom, pan, do whatever you want to see when multiple instruments might be observing, to go, you know what, that seems like a really good time. Maybe I can get my telescope to observe at that same time. Because what happens is whenever we get more observatories involved, typically, the amount of science you do goes up much faster than just the sum of the parts. And so this is completely automated in the sense that once you fill out the Google spreadsheet below, it is automatically populated. In addition to the campaign timelines this way, of course, there's still the old-fashioned sense that if you discuss things via email, that email thread goes back and forth and is saved online as well. Now, the user profiles are searchable. They're honestly not the most wonderful things to look at in the world. They're still very much information-based. So there's great tools like just the ability to email or even private message within the app. There's the ability to share a bunch of information for individual users, like contact information, what type of user groups, where the user groups are often focused around science areas, but could be focused around collaboration groups as well, what fields of research you're interested in, and a tool where you volunteer to list the facilities you have access to and or expertise with, so that basically if you say, I need someone that has this type of expertise, you can actually potentially identify them through these user profiles. In addition, there's a wiki option, which I don't think anyone has really used. And of course, every user will see all their posts in the different forums. So what has SmartNET enabled?
3 minutes.
Perfect. SmartNET enables some very basic things like looking at symbiotic X-ray binaries. Here we show with Newstar X-ray and XMM. These are quasi-simultaneous, and you were able to get things like the spin period. You're also able to do broadband SEDs, where if your source is changing rapidly, simultaneity matters. And for instance, this all the information here was used to basically claim that this source looks to be a new symbiotic X-ray binary. We also do something for instance, the black hole X-ray binary MAXI J1820 plus 070 was the next almost great black hole X-ray binary outburst after V44 Cygni. Alex Tederago will be talking about this next week about the longer wavelength view. I'm just going to concentrate real quickly on some shorter wavelength views. And so this shows a combination of hypercam and I'm blanking on the emission. I think it's nicer, but it might be a different instrument. Might be XMM. I apologize. And we have 6 different frequencies all at once, optical and X-rays. You can clearly see from the inset in the middle of the diagram here that there are some cross-correlations. So you can do things like cross-correlation analyses. You can see a peak at about 5 seconds. Given the size scales of X-ray binaries, that looks like basically reprocessing in the outer disk. There's a peak at 150 milliseconds, likely due to accretion flow to the jet base. And there's this often seen anti-correlation, which we still have no clue what that's actually from. We think it might be synchrotron emitting particles in the hot accretion flow, but we don't know. You can also do things like looking at the cross spectra. So imagine taking a power spectra, but instead take the X-ray ray spectra cross with the optical spectra. And you can see at the different temporal frequencies where you have that constant 150 millisecond time lag, as well as see things like the fact that the lag seems to be increasing with wavelength, which is sort of what we expect, but it's actually much shallower than we expect, so it's not consistent with simple jet models. So these type of observations are really rich grounds for theorists. So when we think about SmartNET and Chandra, this is what I like to think about. Several Chandra observations a year require, and many benefit from simultaneity and/or quasi-simultaneity. Basically, you can start a SmartNET campaign before knowing the times when you're going to observe, and this will serve to get other people interested in adding observations to it with other facilities. Then as you get your schedule more cleared up, you can enter that into the Google spreadsheet, and people can really start planning things in a central resource. And when we talk about SmartNet and you, well, we're looking to add more visibility tools like what Erik Kuulkers is going to be talking about next, probably adding a virtual observatory brokerage to use those tools, and of course pursuing sustainability so this doesn't just become a few outbursts and done type of service. I will admit that most of the early adopters have been in X-ray binaries, but really all are welcome because as a community, we can build this as a tool, we can incorporate the next generation of stuff, and basically make sure that we get the most out of simultaneous observations. Thank you.
Thanks a lot, Greg. So if there are questions for Greg, please write them in the Q&A box, and we will come later to those. Thank you. So now let's go to the next panelist, and let's welcome Erik Kuulkers from the European Space Agency, who will be talking about coordinating observations between ground and space-based facilities.
Yes, hello, good day, everyone. So, yeah, I'm the project scientist for Integral, and we are often involved in coordinated observations with facilities in space and ground-based observatories. I give this talk on behalf of a group in Spain where we came up with the coming ideas. I will present how we did coordinating observations in the old way, then go to the multi-messenger era, and I will present how we envisage coordination in the future. This is something which Greg already showed. I mean, various objects in the universe not only emit at different wavelengths, but they also show variability on different timescales. And examples, as Greg has shown, are X-ray binaries, gamma ray bursts, tidal disruption events, supernovae. And there is not only an increasing interest to simultaneously observe the same target, but also at different wavelengths at the various timescales. And here are some numbers about coordinated observations. XMM, for example, about 12% of the observations are coordinated with other observatories like NuSTAR, HST, Chandra, etc. Integral, for Integral, the number is about 10%, and NuSTAR is doing about 30% of its observations coordinated in a coordinated way. Here you see the increase in coordinated observations over the years for XMM, for example. The graph shows you the simultaneous coordinated observations per revolution, and indeed, the last couple of years, people are more and more interested in coordinated observations. So to manage these observations, you need clear coordination as well as communication. Well, in the old days, I will show you an example how we did the communication with coordination. Again, I will show an example of a black hole binary V4 for Cygni, which went into outburst in 2015. So here is what we did when the source went into outburst. Somebody is sending an email to lots of collaborators. You want to set up observations at different wavelengths, X-rays, UV, optical, etc. Of course, ideally, you like to get something simultaneously, and you realize it's tricky. And then you come up with an ad hoc manual observing campaign, as was put together by Tom Marsh, and Greg also showed this graph. And this is how we did the coordination for V4 for Cygni. And again, as Greg has shown, this resulted in a wonderful observing results. Now, it's not all glory. This is how it also can end up when you're doing ad hoc coordination anti-coordination. So on the top you see integral, and at the bottom you see new star observations. And you see that they are clearly not simultaneously, but just nicely one after the other. Now in 2017, the astrophysical landscape changed. On 22nd of September, the IceCube Neutrino Observatory, they alerted the international astronomy community about the detection of high energy neutrino. Approximately 12 observatories on Earth and in space made follow-up observations, and involved were more than 1,000 people from many countries around the world. Well, the source was a very high energy. The source of the very high energy neutrinos was a flaring gamma ray blazar, and well, you see, because of this nice coordinated campaign, you got a spectrum all over at all wavelengths, basically. Well, actually a month earlier, there was an event which overshadows this neutrino event. On the 17th of August 2017, for the first time, prompt gamma rays were detected, coincident with the gravitational wave, as we all know, produced by colliding neutron stars. Well, this prompted an even bigger collaboration with follow-up observations at all wavelengths from space and on the ground, involving even 17 ground and space-based observatories. And we had to put together about 3,700 scientists. So these events basically opened our eyes to the new window of the universe, and we're now talking frequently about multi-messenger astrophysics. It's becoming mainstream. Well, to manage the various observations, you need coordination and you need communication. So coordination starts with some basic needs. You need to know from each other when can facility X observe what, and what will facility X observe when. Basically, you want to know about target visibilities, so to define common time slots, and you want to have an observing schedule because you want to find a common time slot which best fits all. But nowadays, many ground and space-based observatories provide tools and web info. Well, about 12 years ago, I had a dream. I wanted one calendar with entries on what was observed at a certain day, and I wanted to select the facilities I was interested in. However, the calendar nowadays is almost empty. It doesn't mean the facilities are doing nothing. No, the formats of the web output has changed. And since the calendar is not maintained, it has become useless. So what we suggest, can we do better? I think, yes, we can. The best is when observatories provide their observing schedules and also the priorities of the observations going on in the standard format. And the same holds for target visibilities. So these are called what we call services. Then, when you make them automatically retrievable, you can build tools or clients to access these services. However, you need to agree, of course, on a common standard, and that is why we suggested to use the virtual observatory protocols, because they have standards defined already. So what we proposed was to use the OBSTAP for our purpose, and we created two protocols, one for the visibility information and one for the scheduling information, and they are called OBJ-VisSAP and OBS-LogTAP, and you can see at these URLs where to get more information on these protocols. And then you can build a tool, basically, to view the information. You can access the visibility information. For example, as shown here, you see the visibility information for SWIFT, NewStar, AstroSat, and Hitomi, and then you can make a tool which defines the common visibility duration, and then you pick your optimized time when you want to coordinate the observations. So to conclude, I think we need one format fits all. We would like to have the short term and of course also the mid and longer term schedules in a standard format, and the different observatories can provide, should provide the service. And we also want the visibility output in a standard format as a service. And then you can interface with this information with, by using clients and build tools so that you can build your best coordination tool. Well, at the moment, the status is as follows. We have consolidated already the protocol descriptions, and they've been presented to the virtual observatory, and they are about to accept it. This has cost us many years, but we are happy that we're almost there. Well, several of the high energy observatories have already developed prototypes, and Chandra here is in boldface. They were really very helpful and very enthusiastic in helping us out. We had a demo workshop a couple of weeks ago, and we were able to announce for the first time that an optical ground-based observatory has joined us, the Nordic Optical Telescope at La Palma. And this is basically, we built, here we have an example again of a tool where which we built at ISAC in Spain. So you query a source and you put in the start and end time, and then you get the visibilities for the various observatories, including the NOT nowadays. And you can look at the schedule and then make your best coordinated observation. That's it. Thank you very much.
Thank you very much. We can see some of the challenges in coordination and sharing the data and accessing building services, common standards. We will come to this later in the discussion session. So now let's move on to our next panelist, who is Mansi Kasliwal, assistant professor at Caltech, and who will talk about communication and coordination, growth, and CTF perspective. Thank you, Mansi.
Thank you, Ada, and thank you to the organizers for this opportunity to discuss some thoughts on communication and coordination. We heard some lovely talks by Erik and Greg on simultaneous observations across many different facilities. And as Erik mentioned, I mean, one of the most majestic examples of this is this video that you see playing in the background on GW 170817. It was a campaign like no other in terms of coordination and communication with just about every time domain astronomer out there. So that was pretty fun. Now, I'd like to share my perspective from the perspective of a National Science Foundation partnership and international research and education project called GROWTH. GROWTH stands for Global Relay of Observatories Watching Transients Happen. And this is a ground-based network of observatories. So we do trigger space-based observations on our most favorite, most exciting transients that merit X-ray and UV follow-up in particular. The concept behind GROWTH is that we try to stay in the dark, quite literally. So say our discovery engines are located at Palomar Observatory, but often what we are looking for fades on our timescales. So what we try and do is move westward to continue to follow up and collect data on the transient before the sun rises. So from Palomar, we move to Mauna Kea in Hawaii, then to an international set of collaborators. We have 16 partner institutions spread across the globe, and some new partners as well, and some new facilities that have come online in the last 5 years that we've been running. As I mentioned, our discovery engines are located at Palomar Observatory in Southern California. And there are two discovery engines that supply most of our triggers. The first is this Wiki transient facility. which is on the Palomar 48-inch Schmidt telescope, and it's a focal plane which is 47 square degrees. So it's silicon the size of a photographic plate. And what we do is we image the sky. So you can see a field of view against the Orion constellation to give you a visual. And what we're doing is we're imaging the entire accessible northern sky in G-band and R-band every 2 nights. And we also have a private survey that is at a higher cadence. And as we collect these images, within 7 minutes, an alert stream in LSST in Rubin Observatory format is sent out to everyone. This is also a National Science Foundation funded project here. To complement ZTF in the infrared, we have a small project called Palomar Gattini IR, which is a robotic 30 centimeter telescope with a 25 square degree camera, but in J-band, so beyond the micron. So what we're really looking for are things that are obscured by extinction, things that are really cold, things that are really opaque, such as things like affected by bound opacity, etc. Right? Things that are very, very red is what we look for to try and explore the dynamic infrared sky with Palomar Gattini IR. And this is the thesis project of my graduate student, Kishali Day, that you see in the photograph on the top right there. So once we have these discovery engines imaging the sky and supplying triggers, the growth network comes into play to try and follow up and characterize and get to the astrophysics and astrochemistry of these transients. And the powerhouse of growth is quite literally our youngest people, the students and the postdocs who are smiling no matter whether it's 2 a.m. or 3 a.m. When they're collecting this beautiful data set that leads to the discoveries we've been able to make over the last 5 years. Looking at the agenda for the Chandra Time Domain workshop, I mean, there's been plenty of discussions on beautiful science. So I'll try to keep the focus here for this panel on the communication and coordination aspect and the tools and the software that enable the science here. So I'll try to get the discussion kindled with focusing on 3 challenges. So the first challenge for if you're an optical infrared astronomer is just determining what to follow up. The universe is such a dynamic place that we have hundreds of thousands of alerts every night of something changed that is more than 5 sigma somewhere in the sky in the previous night. So how do you determine what is interesting? What is a good experiment? What part of the dynamic universe phase space do you really want to explore? So the example that I give here is one that has been again hinted at different portions of this workshop, which is multi-messenger astronomy. So we had LIGO Virgo's 3rd observing run, which had very close localizations. Median localization was 4,480 square degrees. But with our large cameras, with both ZTF and Gattini, we were able to map these large areas. Now, when we went and imaged these large areas, and we asked a simple question, what is spatially and temporally coincident with the gravitational wave signal? The answer was not one event, but 2.1 million events that were coincident with the 13 gravitational wave localizations. Now, obviously, these 2.1 million events are not astrophysically related to the gravitational wave trigger. So the first step in the challenge is how do you go from these large lists of things that have astrophysical things that have changed in the sky to what could actually be astrophysically related to the multi-messenger at hand. And we go through this funnel process that you see here, which involves at least 3 different machine learning algorithms to get us to the stage where we have 127 candidates that then require additional follow-up spectroscopy with the growth network, or follow-up photometry with various telescopes in the growth network, etc. And then we can say, okay, this is related, this is interesting, but for different reasons, this is unrelated, etc. So I'd say that first challenge is just determining what is interesting to follow up. And there again, software is critical. These machine learning algorithms that we have to separate the wheat from the chaff, find that needle in the haystack is absolutely critical. The second challenge I'd like to highlight is that, okay, you come up with your 127 favorite candidates, but many of them are fading very quickly or rising or quickly. And you want to be on your toes to collect and trigger the essential follow-up data. So using the same example from O3, one way to organize the follow-up is just to post a GCN circular, which we did during O3, and we posted something like 60 GCNs in O3. And this triggers follow-up from a worldwide community of astronomers that are looking at these GCNs and tying their own follow-up telescopes to these GCNs. And that led to another 140 GCNs saying this one is a supernova, this one is an afterglow, this one is a cataclysmic variable, etc. So that's one way to do the follow-up. But within the growth network, within the set of telescopes that we have, it's a very heterogeneous network, right? This is a set of existing facilities that were strung together in collaboration. So we need to organize this follow-up in a more systematic way. So some of our telescopes are fully robotic. So without touching anything, you want the discovery stream to come in, some systematic definition of candidates of interest, say everything brighter than 19th magnitude, everything coincident with a galaxy within 200 megaparsec. So for those things, we want to automatically trigger follow-up with robotic facilities and not have any other slow step in the way, so that it happens systematically, consistently, and as an experiment. Regardless, all of these things are time critical, right? So for example, if you have a couple of candidates that are the right place, the right time, the right luminosity, with the gravitational wave trigger, you want to be on your toes and trigger spectroscopic follow-up wherever there is night. So you need a web interface that can help you collaborate in an effective manner and collect data from different telescopes, etc. And I'll show you one such tool shortly. The third challenge is to reduce the follow-up data in a timely manner, right, within minutes again, to try and inform your next steps. Which targets are actually interesting to trigger Chandra on? Which ones have a simpler explanation to their origin? So for example, here's when we were doing this gravitational wave follow-up, and I'm trying to keep the same example for the three challenges. We found this really fast fading event, which turned out to be at redshift 1.26. Now that's a bit too far to be associated with a gravitational wave event, but it's quite spectacular because it's an untriggered afterglow of a gamma ray burst. So immediately this sort of spectrum reduction, this is from the LRIS instrument on the Keck-1 telescope, tells us that we need to trigger everything. We need to trigger radio facilities, X-ray facilities to try and confirm and characterize the nature of this untriggered gamma ray burst afterglow that we stumbled upon while looking for multi-messenger counterparts. So let me now zoom in and focus on the tool that helps us do this. As I mentioned before, we are a team of something like 137 scientists spread over 16 different institutions, all with different science interests. So the tool that we use is this completely dynamic collaborative platform that we call the Growth Follow-up Marshal. This is a web tool which is very visual, and it's very similar to say our Facebook page, right? So this is the Facebook page for time domain astronomy, the simplest way to think about it. But the back end of it is a database, and the front end provides many ways by which you can trigger robotic telescopes, both from filtering incoming large streams of data, and from directing and marshalling the follow-up to different follow-up facilities, some of which are much more classical but offer bigger glass, some of which are fully robotic and can get you a spectrum within minutes of triggering with absolutely an end-to-end automation in the system. And with this tool, we've been able to discover and classify something like 4,859 supernovae to date in the last few years here. So this tool here, the Growth Follow-up Marshal, was something that has been developed sort of over the past decade by many graduate students and postdocs in astronomy, in time domain astronomy, trying to do their science. So it's a very powerful, very functional tool, but it's not something that's been written by software professionals. And in the era of the Rubin Observatory, the next generation of time domain surveys, we are feeling the itch and feeling the need to take this into a more, to reach out to software professionals, to make this a more scalable, more adaptable, make it an open source tool, basically. And I'm very happy to report that that is actually happening now as we speak. We are in beta testing mode of a brand new next generation tool that uses the most modern software technologies. For fun, we call this tool Fritz, which is the first name of our favorite leader here, Professor Fritz Vicky. And we have a development team, which is a partnership between Caltech and UC Berkeley. And we have a fully open source. You can go look at our code on GitHub. If you look up Fritz on GitHub, you'll find it. And we're currently in beta testing mode of this new tool, which basically combines two functionalities, two tools that we've been working on for the past few years. One is called Kowalski, which was written by, thank you, Rodolfo, which was written by Dimitri Duev at Caltech. And this tool basically is a sync for the ZTF alert stream, which has a few 100 million alerts and a few billion light curves. And it has external catalogs for cross matches and all of these different machine learning tools that I mentioned. So it combines Kowalski with something called Sky Portal, which uses more modern web technologies than the Growth Marshall tool did. And the Growth Marshall was designed to be, sort of the easiest to use web technologies that even astronomy students and postdocs can write code in. This is actually more serious. So it's more modern web technologies that scale effectively, that are completely customizable. And this was written by Ari and Stefan van der Walt, whose pictures you see on the top right there. So merging these two, we've been able to go into beta testing mode for Fritz, and we go live on November 1st here. So you can see a recorded demo here of different pages, how we scan through candidates, how we identify candidates of interest, etc. And then how do we trigger follow-up of various candidates. This tool is entirely open source here. So we welcome developers to add to this, adapt it to their needs, and use it for whatever follow-up in time domain astronomy they'd like to do. And I think this demo is pretty long, so I won't wait for it to go through. But let me wrap up here and say that software is really the key to effective communication and effective coordination, especially when working with discovery engines that supply hundreds of thousands of candidates a night. When working with telescopes that are again in several tens. And with varying range of capabilities and different locations and different day and night constraints, and for panchromatic follow-up, such as with radio and X-rays for the relativistic explosions in the mix here. So with that, I'd like to say thank you and hand off to our next panelist.
Thanks a lot, Mansi. Lots of interesting science and many challenges again. So the next panelist is Joshua Wing from Chandra X-ray Center, and he will be talking about planning coordinated observations with Chandra.
Great, thank you, Ada. Yeah, so everyone else has given wonderful talks about time domain astronomy and the challenges of coordinating and just getting the data and how helpful it can be. I'm going to maybe, I don't know which direction it is. Maybe it's closer, maybe it's further out, but a little more detailed look at exactly how we do handle these types of observations here at Chandra. So I'm part of the science mission planning team. And so we're responsible for laying out the long-term schedule and the short-term schedule for Chandra, and figuring out where all the observations that we've approved within a given cycle are going to be observed. So I should point out, since this is a time domain astronomy conference, Chandra does have tools for doing time domain astronomy as well. We have targets of opportunity and director's discretionary time observations that you can trigger when an event is has been met. In fact, just earlier this week, I believe we interrupted one of our schedules to respond to a TOO on the order of 1 to 2 days after the trigger. So we certainly are able to do those. We aren't able to do a lot of them. It's limited. In any case, that wasn't what I was going to talk about. That isn't what I was going to talk about today. I'm going to talk about how to do the coordinated observations with other observatories. TOOs and DDTs can be coordinated, and we often do that. But other observations can be coordinated as well and placed in the long-term schedule well in advance. So here we go. So specifically talking about coordinations with Chandra, here's a brief overview of our procedure. So the first thing we do, once all the accepted targets are in and everything has been decided in terms of GO and GTO programs, we then look at all the programs that are requesting coordinated observations, go through then and identify any additional constraints or preferences that those observations have. So either for Chandra or for other observatories, you know, there might be preferences to say at the VLA to observe in a certain configuration at the VLA. So that narrows down our window of when we can observe it. We then communicate with the planners at the other observatories and agree on a preliminary schedule. Usually that's on the order of, well, this works for both of us. Let's do that. At that point, we can place the observation on the long-term schedule, and hopefully there it stays until about 3 weeks before the start of that week. We get in touch with the observatory again and just say, you know, just a reminder, this is when we're observing. Are you still okay with this schedule? 3 weeks is when we start here at Chandra, when we start our normal planning process. And that gives us time to change the short-term schedule if we need to. So that's why the time scale is 3 weeks there. And then once we have a preliminary schedule, we can come to an agreement with the other observatory concerning the final observing schedule. And that's about 5 days before the start of the observing week. So we can make small changes or, you know, within the time scale of a week changes up to that point, about 5 days before the start of the week. So the first question is, how does a proposer request a coordination? So using the Chandra proposal submission website to create a new proposal, and to get these figures down here, I actually created a new proposal last night. So sorry about that for all the data systems people that have now a trashed proposal. These constraints can be applied to each target. Specifically the coordination here, you can select a coordinated observation, and you can, must this observation be coordinated with another observatory? If you select yes, required, that kicks off for us the process that I just detailed. You can request a constraint for coordinated observations of a target already approved at another observatory. So you already have time at the VLA or on NuStar, and you're applying for Chandra time, and you'd like to coordinate those two observatories. Or it can be a target approved for joint observing time through the Chandra review. So you can apply for both NuStar and Chandra time, or VLA time and Chandra time, or all three during the proposal submission through Chandra. There's some information in terms of what exactly that means. Will this be coordinated? The maximum time interval is the other thing you have to set. And so the time interval is the duration, the maximum separation between the start of one observation and the end of another observation. And I'll go into that in a little more detail in a few minutes here. And then you can choose which observatories you'd like to coordinate with. We list that the choices are HST, XMM, Spitzer, Swift, NuStar, NRAO, or ground. There maybe it makes sense to add another one that's just other. Any observatory that we can get in touch with, you know, if this was approved by peer review, then we will attempt to coordinate with them. Ground, space, it's, you know, we'll make the effort the same. So through cycle 21, we had 3 different levels of coordination commitment. So we had coordination constraints, in which we would do everything in our scheduling power to meet that request. We had coordination preferences. So we would meet the preferences as best we can, but we won't rearrange a preliminary schedule or introduce inefficiencies to meet that preference. But generally, if we saw a preference when we were laying out the long-term schedule, we would make sure that the long-term schedule was laid out in a way to meet that preference. And we've also honored unofficial preferences or unofficial coordinations that we treated the same as preferences. And typically these were cases where another observatory would say, hey, you know, we're observing this source. Can you just let us know when you're observing it so we can match our schedule to yours? So starting in cycle 22, which was the recently, the most recent Chandra proposal cycle that we just, well, not just, but we released a new target list a few months ago for cycle 22. So starting in cycle 22 and moving forward, we're only accepting constraints. So this is true for all categories, not just coordinations, but also coordinations. In addition to this, a resource cost is calculated for each target based on the sky location and the selected constraints. So if you had a coordination constraint or window constraint or role constraint, that is all factored into the resource cost. And the Chandra TAC has a limited amount of resource cost to award in addition to observation time. So coordinated observations carry an increased resource cost because it does take effort to coordinate these observations, and it takes coming to a time that works for all observatories isn't necessarily the best time to schedule the Chandra observation. So that is a resource cost for Chandra in that sense as well. And then the coordination interval, the smaller the coordination interval, the more close in time the two observations have to be, and the longer the coordination interval, the farther apart they can be. So the smaller that coordination interval, the more precise coordination we have to do with other observatories. It's much more difficult to schedule a 0-day coordination interval than it is to schedule a 50-day coordination interval. As I mentioned, so moving forward, there are only coordination constraints moving forward. We have a coordination interval, and then we specifically look at what observatories we're coordinating with, and they have special considerations. So are there visibility windows? Is this target only visible at certain times of the year for the other observatory? Are there specific instrument configurations that are required for the other observatory that are only available part of the year? So for instance, VLA only has an A configuration at one semester out of 4. And then we look at the planning cadence of the coordinating observation, the coordinating observatory. So, Chandra has a process where we have long-term schedule and then a short-term schedule, but that spans an entire year or more. But that's not necessarily true for all observatories. So if an observatory that we're coordinating with only has a 6-month cycle, then we will work to get that coordinated observation within the 6-month window that makes sense. So as I mentioned in more detail, the coordination interval, so it specifies the maximum duration encompassing all observations. So coordination interval longer than the longest observation implies no need for simultaneous observations. So in other words, the shorter observation does not need to completely overlap with the longer observation. So here's a diagram of potential coordination scenarios where we have a 1-day coordination interval and a 30 kilosecond Chandra observation and an 8-hour VLA observation. There's many different ways that these two observations can be scheduled to still meet that 1-day coordination interval. So the 30 kilosecond Chandra observation can come first, and then there can be a substantial gap, and then followed by the 8-hour VLA observation. Or we could line up the Chandra observation and the VLA observation, or just have them back to back. And so all three of these scenarios meet the 1-day coordination interval. A coordination interval of 0 or an interval shorter than the longest observation implies simultaneous observation. So the longer observation must completely overlap the shorter observation. So here's another example. If we had a 150 kilosecond new star observation and a 30 kilosecond Chandra observation with a 1-day coordination interval, because that 1-day coordination interval is smaller than the 150 kilosecond new star observation, the implication is that the 30 kilosecond Chandra observation must fall completely within the 150 kilosecond new star observation. But any arrangement here satisfies that coordination interval.
3 minutes.
Thank you, Rudy. So the coordination interval holds true even if many observatories are involved. So this might be a little more complicated. We've got several observatories and a 1-day coordination interval. There's a lot of different ways we can arrange that. But if it's a 0-day coordination interval, it's a little tighter. We have to line up all of the shorter observations. So when we do this, we look at the entire cycle. We look at additional Chandra constraints, primarily thermal. We talk to the observatory. Are there any additional constraints on the observatory? We settle on a time that works for all observatories. And the specifics depend on the coordination interval, as I mentioned. So do we need to identify exact windows, or is a 1 month or 1 week fidelity okay? So one of the things with Chandra, as the spacecraft is aged, thermal considerations are important to keep in mind, as are visibility constraints. So on the left here, this is a source. It's actually 3C273, which is our yearly calibration source for all X-ray missions. We can see that it goes into sunblock here, and it is not visible to Chandra from August through the beginning of November. So we couldn't observe it then. But we also have to take into account the thermal constraints. So as Chandra has gotten older and hotter, we can no longer observe anywhere in the sky for extended periods of time. So if you have a long observation, it needs to be split. So that makes coordinations more difficult, because you're splitting them into smaller pieces, and you need to coordinate all of those smaller pieces, especially if it's a simultaneous coordination. So this is something, when we look at the entire year, this is what we see. Here are all of the observations that are coordinated. Well, not all of them, a subset of the observations that are coordinated for cycle 22. As we place them in the long-term schedule, we note it here. And then we get in touch with the coordinating observatories and let them know where we're looking to schedule it, and if they have any problems with that. The short-term scheduling, we begin about a week before, we begin about 3 weeks before, as I mentioned. We send an email to the coordinating observatory. We have a preliminary schedule about 10 days before. At that point, we can give the coordinating observatory more exact times, in terms of this is exactly when we're hoping to schedule this observation, but we can still, since it's a preliminary schedule, we can still change it at that point. And then we have as I mentioned, we have the final schedule in place about 5 days before the start of the bin. So a weekly mission planner will see, as they're looking at the targets in their week, they will see a page that has all the information about this target. There's a section that details the coordinated observations, and they'll see that, yes, this is coordinated. It is a constraint, and it's coordinated with XMM-Newton and NuStar with a coordination interval of 0.5 days. So that gives them the information they need to make sure that this coordination constraint is met. We also have a page that keeps track of all of our coordinated observations that are scheduled for the current year, and contact information for the observatories, some notes as to what to keep in mind when trying to schedule this in a preliminary schedule. And you can see that we have some coordinated observations upcoming with NuStar, and I believe some of these are also scheduled with NICER, and I believe the PI of one of these is in the audience right now. So hopefully everything goes smoothly and we are able to coordinate. So the end result, if we don't hear from participating observatories, we don't hear from them unless there's a problem. If everything goes as planned, the PI will have data from each observatory taken within coordination interval. And from there, it's up to them to do the science. So for cycle 19, we had about 107 coordinated observations totaling 2.5 megaseconds. Cycle 20, we had 72 coordinated observations totaling 1.9 megaseconds. And so far through in cycle 21, through this point, there have been 48 coordinations totaling 1.4 megaseconds, and we still have some more to do. So thank you.
Thanks a lot, Josh. So pretty challenging. So let's perhaps turn the cameras on for the panelists, if that's okay. Yeah. And the room is open for discussion and questions. So if any attendees have specific questions, please put them in the Q&A section. And I'm going to start with one of the questions that, so it's to you, Josh. So I was wondering, so in these coordinated observations, so you have the Chandra constraints and you have the other observatory constraints. So how is that information brought back to you? So it is, how do you coordinate that part of the?
Yeah, so email.
Email, yeah.
Yeah. So I'm the coordination manager is one of my responsibilities. So I send emails to all the other observatories and ask if they have any constraints, anything that we need to know before we start our scheduling process. Yeah, so it's that low tech. Unfortunately, you know, and I know Erik and Isa have been working on, you know, hopefully a better way to do that. I think, you know, for us in mission planning, I think, you know, I'm sure that's going to be helpful for observers, but for the mission planners, especially for things that can be scheduled months in advance, email is probably probably the quickest way to do it, you know, when you get right down to it.
I see.
Yeah, or you can just use Slack, something like that.
Yeah, yeah, we should get a observatory Slack for all of the mission planners and all the missions.
Another Slack.
Yeah, but this really is one of the things, right? So you were mentioning together with Erik. So there is the possibility of perhaps standardizing certain processes, and others might need still the.
Yeah, especially if one. I mean, if you are coordinating observations with the other half of the world, I mean, they may be sleeping, and you want to see quickly if you can coordinate something. So if you can then get the information automatically, I mean, that's the first hurdle already.
Yeah.
Yes, totally. So I do have.
I actually can ask a question of Josh. I mean, we're picking on you, Josh, but I think it's because it shows that interaction between the observers and versus the mission planning end. And one of the things that strikes me is that you've got a lot of effort that you need to do by what seems like by hand for mission planning for Chandra. So what are the capacities for automating that? Imagine you have something like, all of a sudden Chandra wants to get into the FRB game and wants to be, I know that's in hyperbole, but you want to get into the FRB game and you want to, on the next pass, tell Chandra to go somewhere, and you don't want anyone to be in the loop. Are there capacities? Is there a push towards that in Chandra, or do you guys just not have the personnel capacity to develop that?
Yeah, so I think, Swift exists and was built specifically for what you mentioned, right? To quickly respond to transient sources and without human intervention. They can push up a queue, But if something happens, Swift can just go and observe that source and interrupt their entire schedule to observe this transient source. Chandra certainly was not designed that way, and will never do that. I mentioned at the beginning of the talk, we do have TOOs, which you can propose for, and we have a response category that's very fast, which I think the response is 0.1 to 5 days is the very fast category. 2? Okay. I should.
I may be wrong, but the standard in almost all of astronomy is the weekend, i.e. 2 days.
Yeah. So unfortunately, that we're an older mission. I briefly mentioned our thermal constraints. We'd love to. It isn't a personnel issue as much as it is a mechanical issue. And there's only so much we can do, especially if the satellite is already hot. We need to cool it before we can go to another hot target. And if the source you want to observe is hot, it might just be that we're not going to physically be able to observe that source for a couple of days while the spacecraft cools down. Yeah, so that, I think that's really the thing that, as much as anything prevents us from responding, on the order of 0.1 to 1 day. We certainly have in the past, and we can moving forward, but it as much relies on, the luck of our previous schedule as anything else. If everything was nice, if it's a nice cold target, then yeah, we can get on it pretty quickly. But if it's not, then it might take us longer.
I think everyone understands that.
Yeah. So yeah, and there's only so many of those we can do in a year, because it does take it. It is not automated in the way that Swift is. So it does take manpower or person power to get those things done.
I think that many of the Swift TOs are still manual, right? Only the gamma ray burst and a set of X-ray bursters, for example, they are automatic, but most of the stuff is done manually. They discuss it in the morning, and then the new schedule goes up in the afternoon or evening. We also try at ESA with Interron XMM trying to automate planning procedures, but it's very difficult. As Joe said, many of the communication still goes by email. That's how you reach people.
Yeah, I just wanted to add that the Neil Gehrels Swift Observatory is a fine example, right, of TOs. They've really sort of, in the last few years, done an exceptional number of TOs. Yes. With very rapid response, and that's fantastic for the time domain community. I don't know how they do it. Maybe they don't sleep, but but they are doing a great job.
Yeah, and you need enthusiastic people.
Yeah. So we have a question from Evan Smith, which is addressed to Erik. So, hi, Erik. I believe you started your initiative for standardization back when RxTE was still operational. How many missions have you signed on at this point?
Well, as I said, I started this about 12 years ago. And then I got lost when all the schedules on the web changed. But then we had a discussion at ESTEC. And well, first we had on board XMM because that's next door. And then we talked at various conferences, talked to Chandra, for example, and Newstar. So we have a couple of observatories now on board, as well as the NOT, as I showed, the optical observatory from La Palma. But it takes a lot of effort, a lot of time, patience to get people to use the standard. And also takes a long time to get the standard approved. But once we have that approved, and I think that's going to be done later this year, then we can show basically to the world that the standards are available, and they are rather easy to implement. We had these 2 workshops as demos, and if you want to know how to implement them, you can send me an email, and I can get you in touch with the the people who are more knowledgeable than me in implementing it.
Okay, so you have some users' feedback on that sense.
Yes, exactly. Yeah,
that it's okay. So with this protocol, do you also provide tutorials on how to
yes.
implement it okay?
Yeah. Now we have use cases, for example, so you can walk through, and we have indeed tutorials how to set it up on the computer, on the system.
Mm-hmm. Okay.
Yeah, maybe I should share these web pages at some point, but I don't have them at hand, I must say. I don't know how to share them after the session, but
I'm happy to post them to your abstract.
okay, good. Yeah, I will do that. Yeah.
And I'd be happy also to point them to in the IGR website if that.
Yes. Thank you.
So there is a question for Mansi from Rodolfo. So you mentioned a timeline for sending the GCN alerts. How do you manage data processing and distribution to facilitate that? Are all level of products available or only the reduced products?
No, that's a great question, right? So let me give you very concrete answers to that. So when the first image is taken, it's usually, say, 30-second exposure or up to 180-second exposure. That gets read out in 8 seconds. And then in 7 minutes, all the processing that goes into taking that image, subtracting it with a reference, generating these alerts, and that's done. So that takes about 7 minutes. Then we normally wait for a second observation of the same field in a different filter. So if you've got a G-band image, we're waiting for an R-band image. And that could take anywhere between half an hour to an hour. Once we have information from the two observations of the same field, then many of our machine learning algorithms kick in. And then what we display to the user, to the scientist, is a thumbnail triplet, which is your newest image, your reference image, the difference image, and then a whole bunch of metadata, which are these different machine learning scores, the brightness, the light curve, whatever information we have in sort of a one-row visual. And then we link, so that's answering your data products question, right? So whatever is needed to make a quick decision about whether that source is a go or no go. And then we link to more in-depth questions, right? Suppose it's not clear, maybe it looks interesting, but more detailed inspection is warranted. Then we have something called an examine button, where you can go into the lower level products and look at every single observation in the database associated with that part of the sky and do a deeper dive if need be. So in this entire process, then usually within an hour from the first observation, up to 2 hours, if things are going slowly, you're able to generate the most interesting candidates to post on GCN circulars that merit follow-up for photometrically or spectroscopically.
So ultimately, there's a human involved in the decision to send the circular.
Yes. The GCN submission is not automated because we don't want to accidentally send garbage and risk wasting somebody else's telescope time on something that could be more simply explained as something with the previous episode of eruption, or something that we can understand through existing data in archives or in etc. So we try to only post those candidates on GCNs where we've done all the checks we could based on existing data, and we're still not able to discern the nature of the source. So it remains viable as a potential counterpart to, say, the gravitational wave trigger or the gamma ray burst trigger. So we try to do our full due diligence before sending this out, but we try to make our job as easy as possible, right? Because you can only think so quickly at 2 a.m. So
Can I ask a question? I mean, can you still do the manual checking when you have LSST online and SCA online, for example? You get millions of different objects.
Right. So you want to make it as easy as possible, right? As painless as possible, right? So a lot of it is actually automated, But still, I mean, before we press that submit button, we do want a pair of eyeballs, right? Because no matter what, the follow-up resources are still limited, right? So this is for the GCN question. There are experiments where the follow-up is more dedicated. So we have, for example, a robotic spectrograph on the Palomar 60-inch, which is dedicated to time domain follow-up. So there we have no human in the loop, right? I mean, there, from the collection of the data to vetting the alert, to deciding which ones satisfy the experiment criteria, everything brighter than 19th magnitude, anything near a 200 megaparsec galaxy, to triggering that spectrograph and getting the follow-up data. That's automated end-to-end, right? Because there, that particular facility has the appetite for fully dedicated time domain follow-up. But when we're posting it to GCN, then that is sort of inviting everybody with a wide array of facilities, which are more precious, to take a look and discern the nature of the source. So there we have a higher level of responsibility in making sure every I is dotted, every T is crossed before we post that GCN.
I think you're going to start seeing, with as more people tend to adopt the VO event approach, which I'm sure is how the automated stuff is being done. I think you're going to start seeing different gradations of VO events, which is the sort of the very raw stream, this might be interesting stream, this might be even more interesting stream. And I suspect that GCNs and ATELs may be the final one where, yes, a human has looked at the stream, but not necessarily. I'm looking to possibly automated ATELs and GCNs for things where once we're really confident about it, where it's not, yes, a person has looked at it, but most of the ATEL is going to be automatically written, right? And so as we're all shifting towards larger numbers in whatever waveband, it just has to be much more automated. I mean, I spent, I don't know how many hours for V446. I think I slept 4 hours a night for 4 months and then recovered for 8 months afterwards for that in order to do a lot of the organization. And that's one of the reasons why all these things about working together and coming up with these ideas resonate so well with me, because there's no way I'm doing that again.
Well, that's what you have your students or postdocs for, right? Yeah.
So
there's no way I'm making anyone else do that again either.
So I guess that just to follow up on that, Mansi, you mentioned some of the challenges and the what and the how. So I really like that, putting it like that. And so I guess the filters is a key point for when you have these CTF alerts. Not only the machine learning classification, which is, say, the first filter, but then all the different filter interventions to boil down to creating the final GCN.
Right. So the machine learning scores are like inputs to the filters, right? They're like one piece of metadata that can inform the filter. But the hard part is really the scientists deciding, what is it that defines a systematic experiment? What explores this part of parameter space thoroughly, such that if I get a spectrum of everything in this piece of parameter space, then I can write a beautiful paper, right? I mean, I'll learn something or I'll discover something that we haven't seen before. So I think that definition is where a lot of time and effort is spent.
Mm-hmm. So I do have more questions, but before am I going to that? So there is a question for the panel and moderator. How many of you have collaborated on your various tools?
So I'd say I have not been collaborating on the design, but I've been staying up very much in tune with the project that Erik was talking about. Like I said, that one, the timing of it, and in many ways, some of the ideas of it, I think, came a little bit as an offshoot from the stuff that both Erik did, and then with V446 reminding us, oh crap, we really got to get our act together on this. So I think there is that. There's a certain amount of ways in which we all collaborate, even when we don't all collaborate, in the sense that you see a good idea out there, you often steal it. To be perfectly honest, but I think that does raise a good point that there's an awful lot of us that are developing very similar aspects, very similar things, and what is the optimal way of developing that? And that's a very hard sociological question how to answer. I was messaging Mansi, for instance. I'm very interested in talking to her about the Sky Portal aspect of Fritz, because I need to do something similar for radio data, and I was copying some ideas from a Marshall that was a copy of the ZTF Marshall. So
yeah,
Yeah, so
yeah, I
think
copied that.
also-
Yeah.
Oh, sorry, go ahead. After you, Erik.
No, I wanted to copy that. It's difficult to get into contact with people you don't know. So you first ask your friends, and then friends, and so forth. And then the whole thing starts rolling.
Yeah. And I was just going to say open source code development is really important, right? I mean, because with the first original version of the PTF, IPTF, ZTF Marshalls, it was a bunch of us, students and postdocs writing code. And then that's really hard to try to standardize and try to share and adapt to different needs. So that's why we just did a complete overhaul, right? We just started from a clean slate, started with people who knew what they were doing, right? They were actually trained as computer scientists and really knew how to write good, clean, open source code. Using the most modern technologies available today. And that's what we did with Fritz. And our goal with Fritz is to, the code is already out there on GitHub, and for people to take it and adapt it to their science needs as much as needed, and then contribute to it, right? So that as it grows, it becomes hopefully, a solution that can help out many different sort of sub-communities of time domain scientists addressing this problem from different angles, different perspectives. But I do think that open source code development really helps with the path forward to better communication and coordination across different communities.
Yeah, and you need the right expert to do the right job. Yeah, I mean, I for example, would not have been able to set up the protocols myself. I mean, we had some experts in our group who really know about these protocols and how to set it up and how to present them to the VO consortium and so forth.
Yeah, and the same thing here at Chandra. We, I thought it was a good idea. The director at the time thought it was a good idea to use those protocols, but I certainly didn't implement them. The software engineers here took care of that. So yeah.
Yeah, it comes back to the person power thing that we were talking about.
Oh yes, definitely. Yeah.
Before.
Yeah, when we a couple of years ago we had a big workshop, and people from all over the world basically discussing these VO protocols. And one of the drawbacks people said is people's power.
Yeah.
I mean, you need.
Yeah.
Exactly.
It comes very frequent. So we have another question from Carl Forster. It's from Mansi. Has there been a discussion to include IVOA scheduling protocols, in particular OPS-LOCK-TAP with Fritz?
Not yet, but I hope that, I think that's a great suggestion, and I'm happy to talk to you more, Carl, or Ada. I think you know all about this too, to understand it better. And we're right now in sort of beta testing mode. We go live November 1st. So this is a good time, I think, to learn about this and include it as needed. Yeah.
Yeah, either Carl or I can give you the links to the right pages for that. Yeah.
Thank you.
And thanks. So I was in those lines. What is the experience? So how difficult is it to implement things like that from your perspective, Erik? And to get into it?
Well, I mean, if you talk to the Chandra people, they were the guinea pigs, and it took them quite some time and a lot of effort. But now we have sort of standardized it, and we have these tutorials, and I think within a day you have it all set up. Okay. I mean, the surface. Huh? I mean, then you have to build the tools, of course, to retrieve the information, and that's another job. Yeah.
And if somebody from the IVOA team wants to do a pull request and contribute some code on this, that would be great.
Yeah, I think we have
save us the learning curve.
Yeah, I think we have even the some of the codes available, or the tools. So
okay.
Yeah, we should get into contact with each other.
Okay, that sounds great.
Okay, that's good. So
I'm sorry, we have 5 minutes remaining.
okay, very good.
Or we can talk forever.
One of the things, so we talked a lot about the automation, the computation part of it, and we touched a little bit on the limitations of the person power issue. But I also want to turn this around in that in the end, we do science because we enjoy it. We do science, as an activity, and I don't think we're at the point yet. I joked on the chat that we're not at the artificial intelligence PI stage yet. But even going beyond that, I think when when it comes to like communications and stuff like that, a lot of it is still going to be very much the human touch, and it very much is an opportunity to still stay very involved with the science. In my mind, let the computer do the hard lifting, the computation and stuff like that, and let us use our creativity, our scientific intuition, our scientific experience to make the connections. I mean, that's what I think a lot of us got into here. I don't think many of us got into this and said, you know what I really want to do? I really want to write code to do X, Y, and Z. Some people did, but I think a lot of us got in here to do the science, and I think I think that's actually what we're actually getting into more. Is even though you may spend a lot of time actually supporting developers and stuff like this as you go later in your career stage, you're actually enabling a lot of people to do more science, which is the goal.
No. So I have a question. Mike Nowak. It's not always appreciated outside of Chandra, but thermal constraints always affect the full week's schedule and usually can affect it well beyond that. I was once involved in a TO request, which Chandra did consider seriously, but if accepted literally, would have affected the Chandra schedule for the next 6 months. That can't be automated. Josh,
Yeah,
I guess that's
I think this is going back to the conversation that Greg and I were having earlier in this Q&A. I mean, I think 6 months is, well, certainly, yeah, that's probably accurate, because what ends up happening when we accept a TOO, we have to make room for it, and that means moving one of the other targets in that week. And when we lay out the long-term schedule, it's usually not an accident that a target is placed in a given week. So if we have to remove it from that week, chances are that it's not going to be good to observe. And by good, I mean it's going to make it more difficult to observe at other parts in the year. So it might be that we'd have to wait for another year. Realistically, that doesn't happen, but you can imagine a scenario where it'd have to wait another year to have the best conditions for observing that target again. So, oh yeah, so Mike just said that it was thermally extreme and very long, so literally did affect the budget for 6 months. And yes, so if we kick out a lot of time, yeah, it's got to go somewhere. And that, it gets scattered over 6 months, if not a year. And it is complicated. Yeah. And so I don't know, it's a lot of hand work that, yeah, there's been stabs at making that automated. But, it's not yet.
Well, you still have a job, so.
Yeah.
I may be a bit of a technical optimist here, but there are people whose jobs are to optimize schedules. Like this is an academic field, is schedule optimization. And so I would say that I think that that a lot of this can be done. We may not ourselves have the tools to do it. I think a lot of this could be done, but in the end, there is still going to be a human decision point for hard things. I agree. A thoroughly extreme event that's going to have a long knock-on effect. Your automated software will say, "Nope, I'm not doing this myself. You do it." But you can still have an automated surface do that for catch, the 20% that have to be done by hand, and do the 80% that could probably be done more easily by computer. Sometimes we don't need to let perfection be the enemy of good enough here. And I think that's true for all of simultaneous observations. Like when someone tells me I get a TOO for simultaneous observation, I don't treat it ever as a guarantee. It's always, to me, observatories always do everything on a best efforts basis, always, right? And nothing is ever guaranteed in my mind. I think that's the type of approach we need to have for a lot of things, is that a lot of this is going to be best effort.
Okay, so I think it's time to wrap up. It's past 6:30. Well, 6:30 here. Sorry for that. And it was a great discussion. So I want to thank you all for your presentations and for the lively discussion. And I'm sure that we all have plenty to talk about in the future. So let's keep up with it. And yeah. Thanks a lot.
Yeah, thank you as well.
Thank you. Thanks.
For having me.
Thank you, Ada, for moderating that panel. That was an excellent discussion. Thank you, everyone, for joining us. And I hope you can join us tomorrow morning at 9 a.m. Eastern Time when we start our session on massive and evolved stars. Bye, everybody.